Hello, and welcome to Agrosive Physics. Today is day 84, and what I'd like to do today is look at some instrument equations and do some calculations based on actual instruments. What we'll do is we'll take out the whiteboard, and I'll take out my guitar and possibly a tin whistle or a recorder, and we'll see if we can determine what the wavelengths and frequencies are based upon either the tension in the stringed instrument or the speed of sound in air for the wind instrument. So we'll do a couple of practice problems today and see if we can relate what we talked about yesterday theoretically into some actual practice problems using real instruments. So let's take out the whiteboard now. Thank you. What we're going to do is try to determine the tension when I play my B string on the guitar. And I chose a string that didn't have any wound wire around it. This doesn't have a wire wound around it. It's just plain steel. So as I play the B, what we're going to do is determine the tension that's needed in the pegs at the top. So let's do that now. All right, let's put this theory to practice and find the tension of a guitar string. What I'm going to do is use my guitar and measure the distance between the neck and the bridge. Now you can't see the entire guitar, but we're going to look at the B string. And many of you probably don't have metric rulers at home, so what I'm going to use is my yardstick, and it's in inches, and I'm getting 25 3/4 inches between the neck and the bridge. So 25 3/4. So L is 25 3/4 inches. Now immediately that needs to be converted. And I already did that. And I get 0.654 meters. So L is that value. Now the fundamental frequency would be half a wavelength. So L, which is 0.654 meters, is 1/2 lambda, which means lambda is 0.654 times 2. So using the calculator, 0.654 times 2, I get 1.308. All right, 1.308, and that's meters. So that's my wavelength. Now, what is the string that I played? I played the B string. Now, what's the frequency of an in-tune B string? Now, I looked it up, and it's 247 hertz. All right, so that's going to be frequency. So F is 247 hertz. Now, if we know lambda and frequency, we can do V equals F lambda to find how fast the wave's going, and we multiply the two. So using the calculator again, 1.308 times 247, and I get 323.076 meters per second. So that's 323.076 meters per second. Okay, that's my speed. Now the equation for the speed of the wave on a string, square root of tension over mass per unit length. We already know V. We need to know the mass per unit length if we're going to find the tension. Now, my guitar strings, I had to look this up as well. On the packaging, it said the mass per unit length was the following. 0.708 times 10 to the negative 3 kilograms per meter. So they gave us the standard unit, so we don't have to convert that. So now let's see. 323.076 meters per second equals square root of T over 0.708 times 10 to the negative 3 kilograms per meter. Now the first step is going to be square both sides. That will get rid of the square root. And then we'll divide this side. We'll cross multiply and we'll get, let's do this, 323.076 squared times 0.708 times 10 to the negative 3. And that's going to equal the tension. Now using the calculator, I have my 323 in the calculator ready. I'm going to hit squared times 0.708 second E negative 3. And my answer becomes 73.9, and tension is a force, so it's going to be newtons. Now a lot of times they're going to be listed as kilograms because what I can actually do is set up the same string and then have a pulley and hang a mass on the end and see if I can simulate the same note using just mass. So I would take that number and divide by the acceleration of gravity, 9.8. So 73.9 divided by 9.8, and I get 7.5 kilograms. So if I hang a mass of 7.5 kilograms and I have the distance that's the same as my guitar, I'm going to end up with the B note. So the tension needs to be 73 newtons, which is about the equivalent of 7.5 kilograms hanging from the end of the string. This is the straw flute that I made, and what you'll notice is I cut a triangular piece out of the end of the straw. I flatten it out. And then when I play it, what you do is cause these two ends to vibrate just like a reed would be in a woodwind instrument, and you can create a note. And from that we can determine the frequency of the note using our equations for speed of sound in air and the length of the flute, realizing that it's open at both ends. Whoop. Sometimes the reeds will stick. All right, now let's look at a wind instrument, such as the straw flute. I want to know what note is being played here. Now the way we're going to do that is we're going to take our ruler, and this one I have in metric, but I can't lift it. Here we go. And I'm going to measure from the end of the reed here, which is the end of the triangle, to the end of the straw itself. And I'm getting about 20.5 centimeters. So the length is 20.5 centimeters. And I'm going to get rid of the centimeters immediately, 0.205 meters. Now, because this is an open-ended flute, the fundamental frequency looks like that. And if we remember, it's 1/2 lambda. So the length is 1/2 lambda. So if I go 0.205 meters equals 1/2 lambda, I can double that. So 0.205 times 2, and the wavelength is 0.41 meters. All right. Now, because this is a wind instrument, the speed is based on the temperature, and it's added to 331, and the temperature is multiplied by 0.6. That's our multiplying factor. Now, we're at room temperature, so 331 plus 0.6 times 20 degrees Celsius, and we're going to get 343 meters per second. Well, that's my speed. I have my wavelength, so I'm going to do V equals F lambda. 343 meters per second equals F times 0.41 meters. Frequency equals, so 343 divided by answer is going to be 836.6 hertz. Now that's approximately an A note. I could trim the end of the flute to make it perfect, but this note should be about an A. And what I'm going to do is hit an A on my piano and see how close it is. You can be the judge. What I have here is my jug that I'm going to produce a note by blowing across the top. What I did is I put some water in the jug so that it could produce a little higher note. When I blow across the top of the jug, it's producing a standing wave in here. At the bottom is a compression, and at the top is an open end. So it produces a 1/4 wavelength length, the L equals 1/4 wavelength for the height. As we change the height of the column of water, which effectively adjusts the column of air, we could determine different frequencies. So let's do that now. All right, I want to look at the jug that I played before, and we're going to try to find the note on that. And what I did is I measured the height of the jug from the water line to the neck, where I'm going to blow across the top, and it's about 20 centimeters. And I know I'm saying about, and that's not very precise, but we're going to use that as our example. If we're doing this in the lab, we'd want to be a little more precise. But here's the note. So the jug is producing a note that's quite low, and that's the wave pattern that's going to be produced, 1/4 lambda. And the L, as I said, is 20 centimeters, so 0.2 meters, 1/4 lambda. So I multiply that by 4, 0.8 meters is my wavelength. Now V, still 343. We're at room temperature. And if we do V equals F lambda, we'll be able to find the frequency. So 343, frequency times 0.8. 343 divided by 0.8. I'm getting 428.75 hertz. Now, of course, this value is probably a few octaves high because we're simplifying the frequency of the jug. A larger instrument like the jug will produce a lower note. So this may get us the right note, but it's not going to be in the right octave in this case. We would have to account for the width or in the size of the jug itself. But in a simplistic manner, we use the 1/4 lambda. Now it works for the straw better because we don't have to account for the width as much because it's narrow compared to the length. So when you have an instrument that has a much longer length compared to the diameter of it, so in this case the column of air is quite small for the straw, we don't have to account for the size as much as we would for the jug. But in terms of the note, that should give us approximately the right note, although a few octaves higher. But what I want you to understand is the 1/4 wavelength for doing the calculation, because this produces 1/4 of a wavelength, and we're able to get our wavelength from that value, multiplying the length times 4 in this case, and then doing V equals F lambda to find the frequency. So that's the note of the jug.